Our last topic that we're going to cover before the test tonight is the textbook calls it differential pair with an active load. I'm going to call it an op amp because it's exactly what it is. Okay. So single stage op amp. All right. So everything that we've been dealing with to this point has been a fully differential circuit, meaning that we have some differential input, VN1, VN2, and then we have some differential output, Vout1 and Vout2, and we have been saying that our output voltage is simply the difference of those guys. Well, for an op amp, it's something similar. We obviously have our differential input signal, VN1 and VN2, but we take our output voltage with respect to ground. So in order for us to convert our differential amplifier into an op amp, we need to have some sort of conversion stage that converts our differential output into a single-ended output. There are a couple of different ways that we can approach this, and we're going to talk about two of them, okay? So the first one, and let's just deal with it for MOSFETs. Just for the sake of argument, I'll use a resistor here. ISS, VN1, Vout1, RD. Here's Vout2. VN2. Here's another RD. Here's VDD. All right, so let's briefly discuss how we can make this have a single-ended output. We just take the output at one of them. That's it. The problem with that is that we're only going to see half of our voltage gain, okay? So if we don't take the difference of those two guys, we're going to have some DC shift to our output, and we're going to see that it's amplified only by a factor of 1/2 because we are not getting the full amplification of our differential input signal. We're only looking at the variation on one side of our half circuit, not both sides. So in order to avoid this reduction in gain, what we can do instead is load our amplifier like so. Call this guy ISS. Here is VN1. This will be M1. This will be M2. Here's VN2. This is M3. This is M4. Here's VDD. So right now we effectively have the exact same thing as we have up above, except we're replacing those resistors with a PMOS transistor. So the thing that we are going to change is we are going to make transistor M3 diode connected and take our output at the drain of M2. So what we have done here, in effect, is load our bottom stage with a PMOS current mirror, okay? Now, what's great about this is we're actually going to get the full gain of our differential pair amplifier with this configuration. And the reason why that happens is, let's imagine that we have some load resistor RL, like so. As we increase VN1, or we increase the amount of differential voltage, that means that the small signal level at VN2 has to go down, which means this voltage at this node has to increase. There's less current, so we should see this voltage going up. When we increase our voltage in VN1, we are going to cause our current mirror to draw more current, which is going to get copied. So if the current in M1 increases, the current in M3 must increase, which in turn mirrors in M4. And so we see more current available to flow through that load resistor RL. So in both cases, both current paths serve to increase the current flowing through our load resistor, therefore increasing our voltage output. So our voltage gain for this guy, without any math, because this is the last day and we want to review, is AV is V out over VN1 minus VN2 is GM N times R naught N in parallel with R naught P, where we are assuming that M1 and M2 are matched and M3 and M4 are matched. This is actually more than you needed to know to answer the question on this in your test tonight. This is GMN, so for the lower stage, the NMOS transistors.
And those are in P for lower.
So N is for the NMOS, P is for the PMOS. Yeah. So how does this gain differ from what we would have if we were doing V out 1 minus V out 2? Exactly right. That's the only difference. The only difference between this gain and what we would get from a differential pair, where we were taking the differential output, would be that we no longer have an inverted input. It supplies the exact same amount of gain. So it has identical performance, but we now have a single-ended input, which is what we would expect for an op amp. So in essence, this is literally the most simple op amp you could ever design. It is the input stage of most real op amps. So we start there and then build on top of it to increase the gain to really large levels. Because we know the open loop gain for an op amp should typically be somewhere around a couple of 100,000. And best case scenario, we're going to get maybe 1,000 out of this guy. So we got to bump up the stages and all that kind of stuff later on. But this is an op amp. So, all right, 10 minutes done. Review. Oh, what's up?
Is R naught E just like R naught of the MOSFETs, or is it R naught in parallel with GM?
No, just the R naught P is just the R naught of those MOSFETs. Yeah. If you did the small signal analysis of this guy, which will take the rest of the class.
I was just looking at M3 and I was thinking of like connecting the drain with the.
Yeah, so you're 100% correct there that intuitively it looks like since M3 is diode connected, we should see 1 over GM3 in parallel with R naught 3.
Yeah.
But because 1 over GM3 is going to be much, much, much smaller than R naught 3, it effectively works itself out. Yeah, the textbook does all the math and all that crap. We don't have time for it. So there you go. All right, review time. What's up?
I'm nervous because I went through the web work again and it just didn't seem that challenging. Like I was scared.
So let me talk to you guys briefly about my experience of taking your test yesterday. When I took it yesterday, it was 10 theory questions and 14 workout questions. It took me 66 minutes to do it. One of the questions took me 12 minutes. One of the questions took me 13 minutes. Both of those questions have been removed. All of the questions that are left, the overwhelming majority of them took less than 2 minutes to do.
That sounds moral.
Yeah. Yeah, so that was what Dr. Batari and I were talking about, was if it took me this long to do it, it's going to take you guys, let's say 2 to 3 times as long. So like that would have been almost your entire test spent on one question. So we have scaled back those particular problems. So in one, it was a current mirror where it was the NMOS, converting it to a PMOS current mirror and all that kind of stuff with those extra transistors in place and finding out how much error was in there. And that one took a hot minute. So yes. Yeah.
I was having trouble with those last night.
Yeah. So yeah. So that one took me a long time, and so the emitter follower portion of those have been removed. The other question was calculating a short circuit transconductance of an odd looking op amp and doing it directly. Took a lot of work to get it to be 1 over R-Pi2, which Dr. Batari didn't agree with, and he thinks he's right, and I know I'm right, so we decided to throw it away, just because there was a point of contention. Yeah. Oh, well, the work to show that it's simply 1 over R-Pi2 took 15 minutes. So
just make a bonus question, and you can decide who's right by who gets whichever student gets that answer more, and that's the incorrect answer. That's the incorrect answer, so whichever one comes out more.
yeah. So no, we just dropped that one entirely. So it seems to be a good mix. So it starts out with some op amp based problems, nothing particularly wild or crazy. Basic integrator, differentiator, inverting, non-inverting, all that kind of stuff, a little bit about gain error and all that kind of jazz. Then you get into, I think a little section on, let's see, chapter 9 was current mirrors and cascodes. So yeah, so a couple of current mirror problems, couple of cascode problems, and then it gets into differential problems, with the last one being something having to do with common mode rejection ratio and stuff like that. So it's fairly broad in scope, but none of the problems on the exam to me seem even as difficult as the ones that you did in your homework.
What's like my biggest issue with these things, these questions in general, is like how much qualitative analysis am I going to do versus how much intuitive analysis? Like, am I taking a circuit you showed us and like the gain you gave us, and am I adjusting that, or am I going in small signal?
Option A.
Option A every time.
Yeah, I mean, that's the reason why I beat these things to death, is so that you don't have to.
So it's not overdrawn small signal. That's what I was going to say. So hopefully at least most of them won't have to go like, all right, small signal this.
Yeah, so for the differential pairs and the cascodes and all that kind of, well, so for the differential pairs, I mean, it's going to be fairly straightforward. You might draw a half circuit and say, okay, this is what it is. For the Cascode amplifiers and all that kind of jazz, it's either going to be an NMOS or excuse me, it's going to be MOSFET based or BJT based, and there may be a parasitic resistance or something like that, which affects one of the quantities in there, just like the homework problem where instead of beating yourself to death, say, oh, well, it's in parallel with this particular portion, so I put it in parallel with that in the equation that we derived, you know. Let me make sure I'm not speaking out of turn here. Let's see. So,
Yeah, I assume there will be some, like, if big GM on out, which will need to have a copy.
so the big GM one got thrown out because, again, Dr. Patarg and I didn't agree on it. Finding R out, definitely on there, but it's just using the equation effectively. Yeah, so let's see. Op amp, op amp, op amp, op amp, op amp.
Are there a bunch of non-ideal op-amps?
Yeah, how much?
Because those, I mean, like,
That's more of the actual stuff.
it really is, and we didn't have, I didn't have any homework on
We
it.
did it, yeah.
Like, when you start adding, like, the current and stuff.
Yeah, and
Gain bandwidth product. Okay, so for that kind of, so for the stuff where there were problems, so like effectively for input offset voltage and bias currents and stuff like that, if you did your quiz or participated in the doing of your quiz, you're gold. For the for the other concepts and all that kind of stuff like slew rate, gain bandwidth product and things like that, it's literally a short theory question. So it's circle the correct answer, no calculations or anything like that necessary. All right, so those are all the op-amp questions. So there was 5 op-amp questions. Then we have a question about output impedance. Yeah, and then the gain of a Cascode stage. Then let's see, current mirror, differential, 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 differential. What's that? Okay.
I just want to verify that the MOSFET equation, I guess, for that are identical to the or
Yeah, I mean, the only difference there is that you're not going to have base currents to ever have to worry about. So you don't have to worry about that error that goes into it, right? Because the error is because base currents are drawing some current away from your reference, right? So if we have a BJT current mirror, let me just draw one real quick. We have IRF, here's I copy, let's call this guy Q1, let's call this guy QRef, right? So we know that ICRef can't be exactly equal to IRef because there's base current being supplied from IRef as well. In a MOSFET, we don't have to worry about that because there are no base currents to deal with. So ICRef should be exactly equal to IRef, which would be exactly over to iCopy. Yeah, so for MOSFET, you will be told whether or not there is. That's a crappy looking ground. Oh, well, that's not supposed to be ground either. I'm losing my mind here.
I don't want to hear that. If you can revoke tenure, then I would.
Yeah, not everyone, I think, I
The
struggle
entire
with
time,
that.
one.
Especially.
We did not.
And I was like, okay, then I found it. It was
Wait,
late
one
night.
A?
We did not
Oh.
Oh, okay.
Yeah, the one I didn't know, no, I didn't know.
Except it was because we did it in homework 2, and the only reason I remember how to do
No,
that
but
is
it
looking at
wasn't
his homework
in
2
his
solution.
notes.
It's in the homework 2 solution. So, I mean,
Sorry, Dr. I'm
No, it's fine.
really, I spent like
We
3 hours
did
on that
like,
part of
and
the
problem
question.
2 and 3 probably took me a total of 5. But I spent probably
2 and
4
3,
hours on
number
problem
one, we
1.
spent
The
hours.
three was just-
so I was the exact
Like, where's an
opposite
equation
for like
for
2 minutes. and
Really?
then-
I don't
And
know
then
why, like, I kept
three
looking up, and
took me
like, this
3 hours.
doesn't match things that I have examples of. And then, once I finally got through one, I
I
was
thought,
like, oh,
the
thank
last
God.
part,
The last part.
we're figuring out what I needed to do. I need that.
Yeah.
Because it wasn't specific.
We had a debate. We were on the.
I was asking, I still don't know, I still don't know.
So circling back around to current mirrors here. The current flowing through this branch has to be 0 because there's no current flowing into MREF. There's no current flowing into the gate of M2. So IDREF is exactly equal to IREF is exactly equal to ICOPY. So
Could you give us a version of that example, assuming that there is space current flowing?
okay, so
We have one at home, so that's pretty cool.
let's say we got VDD here. $20 milliamp as IREF. Call this guy QREF. And let's just say, actually, hold on, let me move this. Theta is equal to 100. We want to kind of figure out what I1 is going to be, okay? So for a problem like this, how I would approach it would be labeling things. So I'm going to call this guy right here ICREF. And because I know that QREF and Q1 have the exact same base emitter voltages, that tells me that ICREF and I1 are copies of each other. But we do have to take into account the fact that there is some area scaling here as well, right? So I say then that I1 is going to be 5/3 ICREF based on the area scaling that I see. Because this guy bumps it up, that guy scales it down by that factor of M or N or whatever the hell we want to call it. All right, so I have this current, which is IBREF, and this current IB1, okay? So I can also say no, I'm just gonna leave this alone. So I can say that I'm gonna call this guy IREF and we'll put numbers in later. IREF is equal to ICREF plus IBREF plus IB1, doing Kirchhoff's current law, at node X or Y or whatever the hell you want to call it. So this is going to be ICREF plus IC ref over beta plus 5 over 3 beta. IC ref is IC ref times 1 plus, let's see, 3 beta. So I got to multiply this first guy by 3 over 3 to get a common denominator, right? Okay. So that would be 3 over beta, or 3 over 3 beta plus 5 over 3 beta is 8 over 3 beta. And since I'm trying to find I1, I can say that 3/5 of I1 is equal to IC ref. And then back calculate this all for I1.
1 plus 8 over 3 beta.
Yes.
And then if you didn't ask for that, it would just be the 3/5.
Yeah, so if you were ignoring base currents, the answer would be I1 is 5/3 IREF.
That's all. I don't think they're gonna ask that part. That's too much. We're not there yet. We can only do it. We're all juniors. That's grad level stuff.
So that is a simplistic base current included current mirror problem.
Yeah, right.
All right, what's next?
I think most of it's making sure I have all the formulas and know what it goes to. I have a lot of. I know I'll see something. Right.
Uh-huh. So that's all about the DC biasing and all that kind of stuff, and we literally haven't worried about that at all. We've been dealing with small signal stuff. So yeah, I never once used it on the exam either. So while I'm not saying it's unimportant, I am saying it's not necessary for this. The large signal analysis for the BJT differential pair and the MOSFET differential pair never came up in your homework and is not coming up in the test. We're only concerning ourselves with small signal. I mean, that is literally just about biasing these guys, which at this point is just DC analysis for the most part. So we don't particularly care. That was more about 335 stuff.
What is like common mode rejection ratio?
Common mode rejection ratio is simply a measure of how much good you get divided by how much bad you get, where the good is differential gain and the bad is common mode to differential mode conversion gain.
What is common mode?
So if you have a finite tail impedance, as we proved in class on today's Wednesday, Monday, if for a finite tail impedance and either a transistor mismatch or a resistor mismatch, you will see that a change in common mode signal level causes a change in the differential mode output. That conversion gain is simply the ratio of how much change in output differential signal we see due to a change in input common mode signal.
I think I get what you're saying, but
A, V, C, M to DM is change in VOD divided by the change in VN common mode. Almost positive I gave that to you guys on.
It
Yeah.
is. I have.
Yeah.
I got it.
Common mode rejection ratio, CMRR, is AVD, the differential voltage gain, divided by AVCM DM, and if you wanted to express it in decibels, you just do 20 log of that ratio. And I guess technically,
If you're gonna do it, we'll go over it, so I'd write it down.
This is when you're in this resistance match.
what the transistors don't match, 0%, because that's not in your textbook and it's not in your homework or anything like that. That was just me. Yeah. Not for fun per se. I mean,
No, I get it. I get it. It was interesting. I know.
This will be fun.
Yeah. No, for sure resistor will show up on the test. For sure transistor mismatching will not show up on the test because the other section of the class could not do it. Because they haven't seen it before. Not saying that they're not smart enough, just they've literally never seen it.
I said, if I get on this test, I'm like, I'm gonna have to. I can't write that.
That's amazing.
How do people write that? You get a point out.
No.
And you look at it like this.
I'm guessing we weren't allowed to print out stuff. That was a previous requirement.
Yeah, so I believe it said handwritten in the thing that I sent you guys. Yeah. Front and back handwritten, yeah.
Because I have to like figure, like, it's
See,
spaced
that's
out
the
so
only
I
thing
can see
that
it.
made me I have tiny copies of every screen from the lectures that goes online, Dave on a piece of paper.
Yeah, I mean, the reason why I do that is I used to teach 411 while I was still in graduate school. And I had one really good student who would make out amazing equation sheets and then make copies and hand it to everybody else. And so I'm not saying the other people didn't deserve to get good grades, but they effectively didn't have to do any studying or anything like that. So like students who probably should have failed were able to pull C's because the equation sheet that was given to them was so good. So that's why I require it to be handwritten, no copies and all that kind of jazz.
Perhaps.
So at a minimum, you buddy up with the person who makes a really good equation sheet and you have to write it down yourself.
Yeah.
So you're gonna sort of study.
Maybe let me print them out and just not give them to
No.
because everything is on here.
Yeah.
You know? It's just more convenient.
It's not as bad as last quarter when you can bring all your notes.
All of
Now
those, and
electronic.
I had to rewrite
I wrote all of
them.
it.
Yeah, it's called studying.
Yeah, I mean, but like, still.
I honestly did it myself. I was flip, I didn't even know where anything was my notes.
I got
It was
this
good
stuff
that
that I
everybody
grabbed
was
and
very.
I was like, I am so behind my God.
And then I already moved so quickly, I would have like half the notes here and like, I would be missing something, so like, it didn't.
And then the next time the part was like, it didn't help anybody, so no notes. And I was like, it helps me so much.
The scores did legitimately go down when we let you guys bring all your notes.
I thought that was fascinating.
I don't find it surprising because it makes you feel like you don't have to study at all, because it's like, oh, I have my notes, I'll just look it up.
I think mine is about the
Yeah.
same, but I do remember spending so much time looking through my notebook that I like looked up and I was like, oh my God, I only have 20 minutes left.
Hearing the words no notes inspires a level of productive.
I 100% agree with that, actually.
Only so when you hear no form.
Yeah.
All the time.
All right, what else you got for me?
You can do a differential.
The AVDM, which is like assuming the resistors are the same, felt like that was wrong, but it gave me green.
Yeah, so the differential mode is you assume everything is matched, for sure.
Okay, it just felt wrong. My question on that, I did it to get the correct answer with the resistors, I think that probably like one
Uh-huh.
I guess the way that ended up doing it was that because I chose each one and it didn't work. So I took the average of the two resistors and it didn't work.
So you shouldn't have chosen each one. You should have been, so there's one and then there's one that's got a small change.
Yeah.
Use RD, not RD plus delta R.
I did both of them and they both gave me green, and that was why I was like, this one.
So that one, the current source is
Yeah,
is this transistor
Mhm.
or not parallel for that.
Right.
For R.
Yes.
So one thing that confuses me with that is why on the differential mode model, why you don't place half of that as emitter.
Fantastic question. Okay. So the question is, let's say that we have a differential pair. I'm just going to put a resistor here, RD. V out 1. V in 1. ISS. RSS. V in 2. V out 2. RD. So we have a perfectly matched differential pair, but we have a tail current that has some finite resistance. Since this is perfectly symmetrical, what's the voltage at node X? 0, which means that resistor doesn't matter because it's grounded on both sides. Only when there is a mismatch will that resistor do anything.
And you're doing differentially of that, doesn't matter if it's a
Yes, yes. So that's why you can't split that up into RSS over 2 on both sides or anything like that, because for that to occur, what we would have to have would be degeneration here. That's not what we have. That's a very good question. Yes, that is exactly what you were supposed to do. RSS is the channel length modulation resistance of the transistor. Wait, yeah. So this guy right here is replacing that transistor. That is just the Norton equivalent circuit for this. We know current, it has some finite amount of current and some finite amount of resistance, so we are representing that with the Norton equivalent. Yeah, and this has a fixed voltage of VB3 if this was Q3 or whatever. So small signal, the current doesn't matter. All we see is a resistance, which is just means RSS is exactly equal to R03 because it's a current source. Correct, yeah. If it's perfectly symmetrical, correct. But as soon as we add, then we have common mode conversion gain happening. So differentially, it behaves exactly like a simple differential pair. The voltage gain is negative GM times RD. And I'm saying it's GM times RD because in all of these common mode problems, we have been neglecting either the early effect or channel length modulation in our lower pair. And not ignoring it in this guy, because if you do, then it has an infinite impedance, which means it's a ideal current
Who the
source.
fuck do we call them?
Common mode gain is zero.
I hate you.
Any of that makes sense?
There's a boba tea fundraiser in Centennial Plaza tomorrow. If y'all are interested.
Yeah.
Yeah. So when VA is infinity, RSS
Whenever a white person recommends boba tea, I'm like, no.
have a current.
It seems
I heard
gross
you
to
know
me.
it's bad.
I haven't even tried it.
Or
Oh wait,
Like
no.
sucking the ball.
you don't necessarily have a perfectly matched circuit, but the lack of that resistor there
Oh wait, no. I'm
what is
thinking.
causing all of the common modes
I'm
to be
thinking kombucha.
attenuated. When
fuck
you
is
have a
boba?
finite resistance there,
It's like
then some portion of the common mode
Well, it
signal
isn't
is
even like
passed to the output.
it's a slush.
given to you
Yeah,
by
it's more like
the
a slush.
common
Well,
mode.
it's supposed to be more like a slush. Some people make it like a
Common
straight up
mode to
drink and
differential
it's
mode
nasty as
conversion
fuck.
gain.
Like a drink with a bunch of
Tapioca pearls.
balls, yeah.
Yeah.
Hmm.
Okay. You were having hand gestures. I wasn't sure if you were raising your hand
I
or.
was like,
Okay.
And so, like you said earlier, I guess the
They make it be wine.
I don't know how to spell kombucha.
Yeah, so DM is differential mode gain. So it's what I've been calling AV comma D the whole time. Yeah, that's just differential mode gain. So you can absolutely get that just by looking at the half circuit, either the left-hand half circuit or the right-hand half circuit. Pardon? Ignore the change. Who cares? If the change is small, they're going to be effectively equal.
It's very picky. And it's,
Yeah, use the left-hand half circuit then, because that's what the textbook has been using for everything. That's what everybody seems to use is the left-hand half circuit. Except when you, well, never mind, I won't say about that. That's a 438 problem if you show up there. I won't confuse you further. Sure.
So the output resistance is the same regardless of whichever transistor you input, right? No, the transistor round.
So you're talking about for Cascode Amplifier. Well, Cascode Amplifier, the input should always be on the bottom. Yeah. And you're taking, so. Here's V out. Let's call this VB. Here's VN. And this should be VCC. Sorry, my handwriting is getting terrible while I'm trying to decide whether I'm going to do apparently MOSFET or the other in the middle of this. Yeah. So this is a Cascode. All right. If you had VN here, and VB here, this is no longer Cascode. It is a common emitter amplifier being degenerated by a current source. Cascode means the input has to be applied at the different transistor than the output is taken from.
can you acronym show up on me?
I don't remember.
Can you still use negative GM R out for that?
So negative capital GM times R out, absolutely. That works for any amplifier circuit. Doesn't matter if it's BJT, MOSFET, literally anything. You can do that.
But is the assumption
Is the assumption that capital GM is lowercase gm correct? Probably not.
for non-cascade?
So that assumption that you're saying capital GM is lowercase gm is only valid for Cascodes. I'm gonna have to find my notes real quick, but so you're saying, let's write this down. You have VCC. So let's see, Q4, Q3, VB4, VB3, out, VB2, the in, this is Q2, that does not level Q2, this is Q1. All right, now let me find it in my notes so I don't get all this crap mixed up. Differential pair, Cascode Amplifier. So AV is still negative GM R out, which is going to be negative GM1 times R not or R out N in parallel with R out P, where this is ROP and this is RON, and this is going to be approximately negative GM1 times GM2 R02 times R01 in parallel with R pi 2 in parallel with GM3 R03 times R04 in parallel with R pi 3. So you said, oh no, my subscripts may be wrong. As long as the PMOSs have the same early effect voltage and the NMOS PNPs have the same early effect voltage and the same current flowing through them, meaning that you can say that IC4 is equal to IC3 and IC2 is equal to IC1, subscripts don't matter because this is just going to be R0P, R0P, R pi P, GMP, GMN, GMN, R0N, R0N, R pi N. So the subscripts literally don't matter if you assume that the same current flows all the way down. And the PMOS transistors have the same early voltage, and the NMOS the PNP transistors have the same early voltage, or if it were a MOSFET, same channel length modulation coefficient and same. Ansley, what's up?
Sorry with the hand gestures. I was
Okay. And this is the reduced version where technically, like you would have 1 plus this plus R01 in parallel with R pi 2 and all that kind of stuff, and don't worry about it. It's increasing the level of accuracy of your answer by a small amount while increasing the amount of time it takes to calculate everything by a large amount. So just use the simplified version of stuff.
Is there anything challenging that you want to be something that's like hard, you know, something that's going to be like.
What relevant?
Oh, yes, yes, I just like,
I think some confusing differential.
I know we got some, here's some examples of other things. Because I know we had like this little section of like these things they look confusing to other cases. REE is grounded and anything. We went over that, the generation amplifiers on the bottom.
Right, yeah.
Just divided up too.
RC is replaced by.
Yeah. which for the most part, I mean, it's just find the resistance and then
Yeah.
treat it like everything is in parallel.
I just don't think we're all that great at just looking at a transistor saying, this is the equivalent.
Yeah.
Well, it's like this isn't actually it's actually two different Cascode things, which.
Yeah.
We're talking about this one specifically, but we just mean in general.
Yeah.
Where
I'm trying to think of.
Any poly capacitor stuff, or was that just to help with our project?
Just for the project.
Oh, thank God.
Because I looked at it and I'm like, I don't think this is all.
electric or something like that, the test average would go down 10 points.
Oh, yeah,
Like, just for each word.
Open electric and create something. When you circle away and move on.
I thought
There's no language for all the letters, no letters. I agree, like, once things started going, okay.
Yeah. I thought it was a really cool concept too, because I was like, oh, I got to make it a chip.
Oh, that's a fantastic question. IESB 318 6 p.m.
Yeah, and what was the consensus on how much time we get?
Yeah, I'm not sure what Dr. Brittari said. Like, okay, so for sure the test is designed to be able to be done in 75 minutes. Okay. But I'm not going to be there tonight. But I have browbeat him into trying to give you guys more time for that. So I would imagine that probably 90 minutes or maybe a little bit more than that would be reasonable. 318, the big chemistry, like the place where your first test for, yeah. I mean,
Our lab doesn't get out till 5:30, we go 3 to 5:30. And then we just gotta.
Y'all have.
That is exactly why I didn't take it. That's exactly why I didn't take the Wednesday lab, because I'm like, we're gonna have a test Wednesday night, and I'm gonna not pay attention.
We have to go to Meridian class, then we have time to eat lunch, and then we have lab till 5:30 to exam.
I'm sorry.
My last session got cut short.
All I'm saying is I would rather take a bad grade on a lab, as in like if you don't finish, we're leaving at 4 o'clock kind of thing. I grade on this test.
Yes.
I do say, you'll say, I'll say no one goes.
We've got like an hour, 2 hours.
Yes, I always
So
do.
happy every time. You know, this lab, we don't have to go to.
Yeah, this is.
And for as long as we can get it done.
let me look in the text. So, I mean, there's a problem in here, but we already worked it. It was the one where we took the output at the base, which was difficult, but I mean, that's way beyond anything that you're asked to do on the test.
I will be on your test, so I can't do that here.
Yeah. No, so that was originally a homework problem that we dropped because it was too difficult. And so I said, well, let's just see how terrible it is. It's not bad in the grand scheme of things for the jackass with a PhD to do.
I'll have a lot more questions once I start working on stuff.
Like my favorite question, what is my goal?
I was so confused.
I was told I was doing way too much work, and I'm like.
Well, I asked him a question lab one time and he came and he like put his hand on our circuit, remember that? And he like wiggled it around. He was like just making sure nothing was loose. I'm like, something might have got knocked.
Yeah, that was.
He's just like,
I think he gets anxiety for us. I'm doing this, and then he's like, I don't know. Just tell me something.
I think Vitari's just afraid of giving it away.
like giving away the answer.
Like just giving it
How do
away.
I help without like?
How do I help them without just telling them.
Sometimes anxiety, no matter what it comes from.
Well, yeah.
Anytime I ask him something, he's like, maybe, okay.
Yes, sir.
Fine.
You know, it's funny though, it actually did fix it.
No way.
It was like the, our like sideways looked a little funky, and he really came over and he just kind of, and then it was pretty again, and I
You
was
got
like,
that magic touch, you know?
Oh, you think it's hard to never class those in.
I'd be wrong if I say I don't try it now. Touch it.
I think that's what my parents think I do when I fix electronics.
I just kind of wiggle it around.
Yeah.
My dad is probably better than you in like technology. He does a lot of houses and stuff, like stuff. And he knows I do like some like niche thing. I think my mom would really think that's something.
Yeah, my dad's still believes, but he doesn't. Oh, like he's like. Or like industrial or whatever. So I'll ask him questions. Like, hey,
Neither of my parents were college, so like, they had no idea.
That's what mine is, and I'm also doing read my textbook the other day, and I was like, why would you do that?
No, my dad straight up, like, I made a C on a test, and I'm like, okay, good. And my dad's like, oh, what happened? I passed, what do you mean? I mean, it's good. It's great. Yeah, you know, he was like, what happened? I'm like, oh, I passed. I'm proud.
My parents and I have this like professional game that we go on, and it's always like, hey, how's school going? And then it's all them nodding, smiling, not understanding at all what I'm talking about.
Like, smile away, boy.
Yeah.
My mom does it when I talk to her.
The more understand things get to be. As long as you got your scholarship. it's all that matters.
Well, when you're a kid, you don't get your scholarship.
So how are you gonna be here? You gonna be here for 50?
So this is my, next year will be my fourth year here, but I transferred over here after freshman year. Started in the freshman program here, so
Where'd you go?
I went to both.
All right.
I was gonna be biology.
So this guy looks mean. Let's do this.
Oh, boy.
Hell yeah. That looks disgusting. Oh my god.
That's right, that's what we're doing.
Sure.
Right,
No,
no,
there is current. Hold on. This is going on.
All right,
I
let's
need
see
my
it.
brain power to test.
Just gonna confuse you.
I don't know. All right, so let's break this thing down into digestible chunks. What is happening with M3 and M4? So are they NMOS or are they PMOS? Let's start there. They're NMOS.
They're NMOS and they're diode.
So NMOS, so they're diode connected. So each of those looks like a resistance of what?
1/GM.
Right, all right. So we have now simplified this guy to 1/GM in parallel with R naught. And over here, another R naught in parallel with 1/GM. All right. Here's V out 1, V out 2. All right. We have that resistance RSS there. What's going on with it? Something. Split it in half. All right. So RSS over 2, combining our tail currents to be 1. RSS over 2. VN1, VN2. All right, what is that resistor RP doing? We still have those guys. So let me throw that here. So small signal, what's happening with RP? In parallel with R01 and R02, okay? So from this small signal model, we have, and when we look at our half circuit, we are going to have a common emitter amplifier being degenerated by a resistance of RSS over 2, where R0 is in parallel with RP. And we also have this guy up here. So let's just say, for the sake of argument, that channel length modulation can be ignored for everything, okay? I'm doing that because I know that a common emitter amplifier with degeneration is in the back of the book, so I don't have to go looking through a crap load of notes that are probably in my office. So with CLM ignored, the voltage gain for this guy is going to be negative 1 over GM divided by 1 over GM plus RSS over 2. I'm done. That's from analyzing the half circuit. Oh, actually, I take that back because we do have the RP is going to show up in there as well, but because it's, and I can't do it that way. So that would be what it would be if the RP weren't there. With the RP in there, you would need to adjust accordingly. But that's something that you can do because we're running out of time and I don't want to. But on simple stages like that and saying, all right, so let's start from the top and work our way to the bottom. What the hell does this thing look like and what can we replace it with? That's something simple, right? We took these M4s and we changed it into just some new value of RD that happened to be R0 in parallel with 1 over GM because we know how that behaves. We know that this RP is going to be, because it's placed between the drain and source, it's going to be in parallel with R0 if channel length modulation weren't ignored. It's going to take the place of R0 if channel length modulation is ignored. We split up this resistor along the axis of symmetry to make it look like a simple differential pair. That's as hard as, this is significantly harder than the exam. And we theoretically got everything finished in a couple of minutes. After this, it's just mathematical manipulation.
Did you write that equation again?
Yeah, so, yeah, so if we have, just for the sake of argument, a resistor RD, taking V out here, with lambda equals 0, our voltage gain AV is negative RD divided by 1 over GM plus RS. Literally, the back cover of your textbook has voltage gain equations for common base, common emitter, then common emitter with degeneration, then common base, and then emitter follower, and then similar for MOSFETs. So all of these differential pairs are all based on roughly common emitters with or without degeneration, so it might be good to write those two basic guys down. But you shouldn't see anything that is common base or emitter follower or common gate or source follower on here. If these were BJTs, what would be different? There would also be an RPi that we'd have to care about somewhere. That's it. That's the only difference. The analysis would be the exact same thing. The diode connected transistors up here would still look like R0 in parallel with 1 over GM. We would just have a resistance of R pi between the base and, or yeah, the base and the emitter down here. It's the only difference.
There's no R pipe.
No. For a diode connected, let me go back to my notes where we reviewed diode connected current sources and, or excuse me, transistor current sources and diode connected transistors. Okay, no, I see what you're talking about. Yeah, so for the diode connected BJT, there would be a R pi in parallel with R naught in parallel with 1 over GM up top. Yeah, you're right. All right, what's going on? You good? Slightly better. False confidence. All right, well, hopefully by 6 p.m. it'll turn into true confidence.